Okay, guys, we got today we're going to be talking about quadratic functions and different pieces about them, and when we change certain pieces, how it affects the graphs. So here is your parent quadratic function. The vertex of the parent function right there is at 0, 0. And you also have an axis of symmetry of x equals 0. And the most basic one here is kind of like y equals x squared or fx equals x squared right there. It's going to have a lot of similarities to the absolute value functions that are shaped like v's. These are a little bit more curved, but notice here if you have a negative out in front, just like the absolute value graphs, it flips your graph upside down right there. So we call that a reflection. All right, and then what's a little bit new here, you actually should have learned this in Algebra 1, but if you put a number out in front, it can change how wide or how narrow your graph is. So like typically an x squared graph is kind of like that right there. So that 2 on this one here stretches you out vertically, and we call that a stretch. Okay, and then out here in front, if you have like a fraction right there, so like 1/2 or something that's smaller than 1, and that's what this means, between 1 and 0 right there. Usually you're going to get a little bit of a wider looking graph, and we call that a vertical compression. And both of these are considered vertical here. That might even be good to add. So it's a vertical stretch and a vertical compression. Okay. And then yeah, so notice if you have greater than 0 for your a value, that makes it open up. If it's less than 0, it opens down. We kind of saw that in that first example. But the vertex stays at the same spot. So, also minimum and maximum values, just like with the absolute value graphs, the minimum is the lowest y coordinate, and then the maximum is the highest y coordinate of the functions there. So we're going to graph this first one here. We got 1/3 x squared. So this one has this 1/3. So first of all, that 1/3 is going to reflect. And then the 1/3 is going to be, since it's a number less than 1 right there, we're going to say that's a compression. And what that literally does is it makes everything 1/3 as high. So typically with like your parent function, if you go back up here, you have like points like this right here. We'll write the table off to the side. Typically, you're going to have something that looks like this. So 0 squared is 0, 1 squared is 1, 2 squared is 4, -1 squared is +1, and then -2 squared is +4. So what a vertical compression does is it takes every y value and makes it 1/3, or whatever the number is. In our case, 1/3 is high. So we can go and take that same table right there and then just do 1/3 of it there. So if you go like -2, and actually I'm going to go to -3. So -3, -2, -1, 0, 1, 2, and 3. Because some of them are going to come out super clean. So if you go 0 squared times 1/3, that's going to get us 0. All right, if you do 1 squared, that's going to be 1, but then -1/3 times 1 right there, it's going to get you -1/3. Okay, if you do the same thing with 2, 2 squared is 4, but then -2, 2 times -1/3 is going to make, or 4 times -1/3 is going to make -4/3. So that's kind of a weird number there. So that's not very good to graph on those. And I think you get -1/3 here as well, and then -4/3. So you got that symmetry. So the reason I chose 2 is because that's going to come out real clean here. So if we do -3 squared, that's going to be 9, but then we can do -1/3 of 9. So 1/3 of 9 is 3, so -1/3 of 9 is -3. So that's going to be a real nice point to plot here in a second. Obviously 0, 0 is not too bad. And then 3, when we go and do that, 3 squared is 9 again. And then -1/3 of 9 is -3 again. So those are going to be some nice points. I'm going to go ahead and plot all those. So 0, 0. So we had -3, -3, +3, -3 like that. And then if you want to try and get the -1/3, it's kind of hard to get perfect. 4/3, it's a little bit more than 1. It's kind of like that right there. So it's real hard to get it precise. There you go. But here in a moment, I'm going to let you know exactly what you're expected to do with and without a graphing calculator. On a problem like this, you could go and use your graphing calculator. I have it pulled up right here, and then go and actually look at the table. So as far as steps go, I guess you can say you can just make a table, or I guess use a graphing calculator. And then usually I start at vertex and then just kind of get some extra points around the vertex from there. What does this follow-up question here say? What can you say about the graph of the function fx if a is negative? So if a is negative right there, that means it opens downward, like we saw. And you could even say, because of that, the vertex is a maximum. And then there you go. So not too bad there. Making the tables a little bit tricky, but most of the times you're going to have a graphing calculator with that stuff anyways. Now, some things you can do here. You can do your translations right here, and these work the same exact way the translations work on the absolute value graphs. Instead of the bars, though, this time, we have parentheses, and then we got that square thing. So the square part is what gives it the U shape. And then minus h means right. And then if you add x plus h squared, that would move your graph to the left. And it doesn't matter what h is. And then notice here, if you have minus h right there, the vertex is h comma 0, which just basically means the opposite sign. Okay. What about here with this one? Oh yeah, so when you got a plus number outside of the parentheses, if you don't have parentheses, they're implied to be there. But if you have a plus k right there, that moves you up. And then also if you have like minus k, so I'll write that example down here, x squared minus k, that moves you down. Okay, and you don't have to worry about opposite signs with this really. The only times you think of opposite signs is when it's inside of parentheses. Okay, so this last one here, I guess, has got two of them going on here. So it's minus h, so that's to the right, and then plus k, that's up. So sometimes you can have two pieces there. Notice here that the h is the opposite sign, and then the k is the same. So let's do this here. Let's write opposite here. I'm just going to abbreviate it, and then the same for k. That can help us graph them. Now, with the parent function, whenever a is 1, what's nice about it is that these graphs follow this same type of pattern where it goes like over 1 and then up 1, and then you can go over 2 and then up 4. And they're always going to follow that pattern right there if a is 1, because that's going to speed up some of the graphing that we're going to have to do here in a moment. So, like on this one right here, our a value is 1, so it's going to follow that same shape as the parent function. This plus 3, since it's not inside of parentheses, that means it goes up 3, or at least a vertex. So instead of the vertex starting there at 0, 0, we're going to go and plot it up here at plus 3. All right, and then the rest of the graph right there, you go over 1 and then up 1. You go over 1 to the left and then up 1 right there. And then if you go over 2 and you square that number, that should be up 4, which it should be about right, there. I'm guessing pretty close right there. And then you can draw your graph, draw your arrows, and then you're good to go. Honestly, they should have made that one minus, so we had room to graph it, but that's okay. This next one here is actually a better example. So this plus 1 inside the parentheses, just like with the absolute value graphs, it moves you to the left one. And once again, like I said in those lessons, you just need to memorize that rule. And once you memorize it, it's not too bad to graph these here. So that moves our vertex here. Our vertex is at -1, 0. And then we're going to follow that same pattern. Since the a value out here in front is implied to be 1, you're going to go over 1 and then right 1 from your vertex. You're going to go over 2. If you square that number, that's up 4. If you go over 3 for whatever reason, you would go up 9, like real high up there. Obviously, don't have enough room to graph it, but usually 5 points is going to be good enough if you can fit them. Just make sure you label that vertex where you can see it real well. And yeah, that's about it here. I guess they'd say, how is it a translation? So this first one, we can say it was up 3 units. And then we can say this other one here was left 1 unit. So this next section here kind of goes into the vertex form. Yeah, so I mean, it's kind of all the same stuff here. The vertex, when you have your vertex form right here, is H and K. H is opposite signs because of the negative right there. A determines if it opens up or down. And, oh yeah, your axis of symmetry is always your X value of your vertex right there. So I think that's all. That's right there. So let's see what we got here. What are the vertex axis of symmetry minimum or maximum and domain and range of this function right here? So you're going to get to where you need to be able, without a calculator, to identify the different things here. So I know that vertex right there, that's going to make us go left 1 right there. So it's kind of like a negative 1 is at H right there. The K is 4. So remember, opposite side and same side. So 1 and 4 right there. So that moves us up. And then this 2, it kind of does 2 different things. The negative flips your graph. So does a parabola open up or down? Well, if it's flipped, it's going to be opening downward, which means you're going to have a maximum. So let's see here. I guess there's not really a spot to write that, but you can say it's a maximum. I guess I'll just circle it up there. Axis of symmetry, we say it's the X portion of our vertex, so it's X equals negative 1, and then the vertex was negative 1 comma 4. And then I guess, let's see here, domain and range. So domain is pretty easy with all of your quadratic graphs. They go left and right forever. If you look at every single one here, they technically all go left and right forever. So we're going to say domain is from negative infinity to positive infinity. So, whoops. So that would be a parentheses, negative infinity to positive infinity. And then range, you got to look at the vertex to figure out what's going on with the range. So if it opens upward, we're going to say our values start at that vertex and then go towards infinity. And if it's opening downward, like maybe that first graph we saw, something kind of like this right here, you're going to say it's going from negative infinity up to the vertex point. So range will be a little bit different here on these here. So since it is opening, I guess they didn't give us a graph here, so it's opening downward at negative 1 comma 4, so something kind of like over here. You can draw your little arrows there, so that means your range starts at negative infinity and then goes up to positive 4. And then I'm going to put a bracket around 4 because we're including 4. And I guess if you want to label your axis of symmetry, you can do that as well. And there you go. That would be your graph right there. And I guess we got part C. Oh, okay. I see what happened here. The page got cut off here. So I guess we'll go and copy that over here in a second. Evaluate the function for 2 values of x, plot those points, and then reflect them across the axis of symmetry. Okay, so that's if you were to graph this without a graphing calculator. This would be all your different steps here. So evaluate, yeah, we'll do that. Okay, so here's what they mean by that. We're going to make a table here. And since we know the vertex is at negative 1, 4, we want to stay kind of near that. Yes. Now, always a good number to go plug in and see what's going on. It's 0, because 0 is very easy to plug into that function. So I'm going to write it up here at the top of the page so we have it. Negative 2, x plus 1, and then plus 4. Okay, and then we're going to see what happens when we plug in 0 first. So if we go -2, 0 plus 1, and we got to square that, and plus 4. That'll be -2 times 1 squared, which is 1. That'll be -2 plus 4, so that'll be +2. Okay, now since we have the axis of symmetry means we're going to have the same thing on both sides of our vertex. So if we go over towards -2, we should get +2 as well. And that's what it means by plot those points and then reflect them across the axis of symmetry. If you're not sure what I'm talking about here, if I plot the vertex right here, that's your vertex, and then the axis of symmetry needs to cut through that, just like that. And then we're saying, okay, if we have a point at 0, 2 right there, we better have a point over here on the other side of your axis of symmetry. So you just flip it across and then you're good. All right, so I try to keep the numbers small when I'm plugging in, so let's go see what happens when we plug in 1 into this equation. So that's -2, 1 plus 1 squared, and then plus 4. So that's -2, that'll be 2 squared. We got to use our order of operations, so that means do your exponents, do your parentheses, we did that first, and then exponents. So that's a -2 times 4, and plus 4. So that's a -8 plus 4, which is a -4. So apparently when I plug in 1, I get -4. It's going to be way down there. So because of the axis of symmetry, you're going to have another point over here, and then you can get your graph. Now, sometimes you're going to have graphing calculators, so don't over stress about that. Usually we give you the ones where like your A value is 1 and it kind of has that same shape, kind of like these two that we just did. So that'll speed up the problem here. So we did a part C, we drew the parabola. Does it have a max or a min? It has a maximum, so it goes up to that highest point, and then domain and range, I guess you can copy that back down if you would like. Let's see if I can fit it in here. There you go. All right, so that's that there. Using vertex form, what are the steps to transform the graph from y equals x squared to this right here? All right, so you got a couple of things right here. The +2 means it's going towards the left 2. -5 means it's going down 5, and then this 2 right there is a vertical stretch right there. So let's go ahead and fill this out here. H is technically -2, opposite sign, and the same side. So we can say it's a vertical stretch. H is a translation, is the fancy word for it. So it's a translation, I guess, left 2. And then it's a translation down 5. So just know your rules, and that will speed those problems up. Okay, graph this function right here. So you could use a graphing calculator. I'm just going to quickly do the table here for it. Now, since it doesn't have anything inside the parentheses, it's not going left or right, but then you got the -3, so it's moving your vertex. So you can say 0, -3. Okay, now as far as other nice points to plug in, I guess we're going to do 1 and 2, and I guess -1 and -2. Now we already kind of know this -3 out in front. That's going to, first of all, flip it, and then it's also going to make a narrower graph, or you could even say a vertical stretch. Let's see what happens when we plug all that in. Let's use a different color, kind of differentiate it. So it's -3. And then I guess we're going to plug in 1 first. So that's 1 squared, which will be 1. 1 times -3 is -3. And then minus another 3, it's going to be -6, I guess. Okay, and then because of your axis of symmetry, you'll have -6 when you plug in -1 as well. Okay, and then let's see what's going on at 2. Oop, I'm struggling here today. All right, here we go. So that'll be 4. Oh, whoops. It'll be -3 times 4. And then that'll be -12 minus 3, which doesn't even look like it's going to fit. And then we get -15. So I guess if we wanted to, we could go scalar graph, but we'll probably just focus on those points right there. So it's at 0, at -3. And then oh, well, if I can count, we'd be in good shape. And then 0, or -1, -6, and then 1, -6. So a little bit off the graph here. Try to make it not like a V, kind of like I did, if you can get some curve on it, that's kind of what we're looking for there. Label your points and you'll stay out of trouble there. All right, now then I think the rest of these here just kind of asking you to like compare them or take what you got and change them here. So write a quadratic function that has a translation 2 units up and then 3 units to the left of this function right here. So you already start out with something here. Nothing in the parentheses is making it go left or right. So we're going to just take that x inside and we want 3 units to the left, and left is usually plus inside. So then we're going to put a x plus 3 inside of your parentheses. Okay, and then what else do we have here? 3 units to the left and then up 2 units here. So it's already plus 35, but then we need to go up 2 more units. So then we're going to say it's plus 37. And I don't think they have anything else, so we're going to keep that -2 out in front, and then that would be your new function right there. So you just take the individual pieces and then you figure out what you need to change. Okay, determine whether this function has a minimum or maximum, and then identify the minimum or maximum value of the function, and then explain, I guess. Okay, so to tell, if it has a minimum or maximum, look at your a value. So that's considered positive right there. So it's positive 0.25. So if it's positive, it's got to be opening up somehow, kind of like that right there. So that's going to be a minimum value. And as far as what the minimum value is, it's usually going to be your y portion of your vertex. So this vertex here, right 15, up 10. So 15, 10. So like we said, the maximum is going to be the piece of your y, the y piece of your vertex right there. So we'll say the minimum is 10 right there. Or I said maximum there, I meant minimum. So it's minimum of 10. I'll explain, kind of already did that, so yeah, we're good. When does a graph of a quadratic function have a minimum value? We can say this is when the a is positive, or you can say when a is greater than 0. Sometimes they'll write it that way. Right there, so that's it right there. Is this thing right here a quadratic function? Well, this one's kind of a trick question here because we do see the squared stuff here, but notice you have a 0 out in front. And technically, if you do 0 times anything, you're going to get 0. So this is like 0 plus 3 right there, which is the same thing as y equals 3. And the line y equals 3, we've graphed that maybe a few times by now. But y equals 3 is actually just a horizontal line at 3 right there. So is that a quadratic function? No, I would say no because of the 0, I guess. 0 times, I guess, anything is 0. And you can say there's no more x squared, I guess. So, yeah, that would probably be good right there. All right, so not too bad there. Most of this is, ties into what we've done before here. Now, these two examples here, these are a little bit trickier. These are probably as tricky as we get today here. So you have the vertex of a dolphin's jump is 2, 7. Suppose the path of the jump goes to the point 5, 5. What is the quadratic function that would model this path? So this is something you'd be expected to do without a graphing calculator. And it needs to look like this here. We're going to write it. And since they told us the vertex right here, we're going to put it in what we call vertex form. So that x minus h squared plus k right there. Now the whole idea is they told us specifically the vertex was this point right here. So that's our h and k right there. So we can go and actually write most of this here. The only thing we really don't know is this a value. Now to get the a value, we're going to use the fact that they gave us another point here. This will tell us like kind of, I guess, like how curved the graph looks here. And what we're going to do here is we plug this in for x and y. Okay, so if I go plug in for, I guess, x and y, and then h and k, the only thing I don't have plugged in for is a. And then we're going to solve for that a value to figure out what it should be. Okay, and then after that, we can actually write an equation. So let's go ahead and start putting it all together here. So let's say for the y value is 5. And actually, let's do this here. Let's write the function right above it, just so you guys see exactly where everything came from. Okay, so a, we don't know what that is. X was also 5, happened to be the same. H was 2. And then k was 7. Right, and theoretically, now we can go and use algebra and solve for a. Right, but we do need to follow some of our order of operations there. So you got 5 minus 2. So that'll be 3. That'll be 3 squared. So 3 squared is 9. So I'm going to write it as 9a. So 9a plus 7 then equals 5. And then now this is looking like something from, day 1 of algebra. We'll subtract 7 from both sides. That's negative 2. And then divide both sides by 9. That gets us a is negative 2 over 9. Okay, so then once you get that, that's not technically the answer here. You're trying to find the equation that's going to go through those points here. So we're going to take this a, and we're also going to take this h and k, and then we're going to plug it all in. So we'll put y equals negative 2 ninths. X we're going to keep as x. Same thing with y. And then we'll go x minus 2 for the h, and then the k was 7 right there. And that would be your equation in vertex form. I went and actually added this extra example. I'm not sure if this is updated in your notes, but it's good to do a second example since these are a little bit tricky here. So we're going to do literally the same thing. I forgot to say on this one here, the vertex is 5, 8. And then the point, I'll just put a P for that, is 6, 16 there. So I left out that crucial information. So we're going to write an equation that goes through these 2 points here. So I'm going to write out my original generic form. And then we're going to go and plug in the vertex and everything. So what do we have here? So x, y, and h and k. So we're going to put 16 over here. We're going to have a, which we don't know. Okay, we're going to go x, which was 6, and then h, which was 5. And then plus, squared, and then plus the k value, which was 8. All right, and then we're going to start to simplify down here. This will be 16. This will be 1 squared. Okay, so 1 squared is 1, so 1 times a is just a right there. So a plus 8 equals 16, and then subtract over the 8. That gets us a is 8 right there, actually. Happens to be the same number. There's, that was kind of a coincidence. And then we can write our generic equation now that we have our a value. So we're going to put 8. We're going to go x minus 5 squared, and then plus 8, I guess. And that is it. And I believe that is it for your lesson today. Yep.